name is Alexander Gabriel from TNO, and today I'm going to talk about our demo paper for MMSys 2020. The name of the paper is VVC bitstream extraction and merging operations for multi-stream media applications. So, let's start. In this presentation, I'll talk about the use cases we want to tackle, the drawbacks of HEVC, what VVC can do to help us out, and then I'll talk about the demo itself. The use cases we're looking at are use cases where you might have multiple video streams and want to output one video, or where you might have one video and want to extract a subsegment of it. The disadvantage of these use cases is that typically you will have to have multiple decoders running on your client, and that can be quite resource intensive. To be more specific, the use cases we're thinking about are aggregation streams and extraction. The aggregation could be something like teleconferencing, where you might receive multiple streams from multiple users, or in 360 use case, where you might break up the video and only send the parts where the viewer is actually looking. Then, when you have large panoramas, you might want to extract certain sub-parts of it, and that's the other use case we're looking at. The use cases I just talked about can be achieved using HEVC tiles. HEVC tiles were originally made for encoding and decoding parallelization. This means that a lot of flags need to be sent constantly for in-loop filters and motion vector constraints. On top of it, the tiling structure that is allowed in HEVC means that tile partitions must go from the top to the bottom and from the left to the right, which means that there isn't as much flexibility as one might desire. On top of it, you might have to rewrite parameters all the way from the VPS to the slice segment header, and that can be time-consuming and tricky. Versatile video coding, VVC, or H266 is currently being standardized by the JVED group, which is run by ITU and MPEG. It has a lot of different functionalities, and the main ones that are important for this demo are that you can now have multiple layers within one bitstream, and you can have independent layers within a bitstream. What we've done is we've explored how to indicate the spatial relations between these layers, how to decode these layers with one decoder, and how we can then assemble the output in a decoder. As a side note, we are also working in JVED to get this standardized. So let's take a look at the architecture. So we start by encoding the content, then we merge bitstreams, and then we decode the content in one decoder. So what we do is we take two raw files, run it through the VVC encoder, two VVC encoders to be precise, and we do this with a shared config file. Then, with the two bitstreams, we put them through a stream merger, and we get as an output one merged bitstream. This merged bitstream can then go into the decoder, and the decoder will output one video. So you can imagine, as you can see here, a client receiving two video streams, and the output of the decoder actually only being one video. It's important to note that this stream merging can happen both at the client or somewhere in the network. Let's talk about the signaling used. So the first thing to note is that when we merge bitstreams, what we're actually doing is taking null units one by one from each of the streams and merging them into an interleaved bitstream. When we do this, we also add signaling to the VPS, and that signaling, as you can see right above me, is north, east, south, and west identifier, or the top, the right, the bottom, and the left. What this does is it allows us to know how the layers are spatially correlated, and I'll explain that in a bit. What you can already see is that the rewriting scope is much smaller than before, and it's only the VPS. So let's look at an example. Let's say I have input 1 and input 2, and I want the merged output to look like this. What I have to do is guarantee that the left and the right indicators have the same value, and this will indicate that these sides are next to each other. What you can already see is that the remaining values are 0, which means there's no spatial correlation with any of the other layers. We've also had to make some changes to the decoder. Now the decoder supports decoding multiple layers at the same time. It does this by launching different decoding instances within one decoding process. It's also important that the decoder reads the parameter sets and creates an appropriate sized buffer. Let's take a look at the stream merger in action.
So in this example, we're going to put FF1, FF2, and then FF1 again. You can see in the command line that we have connected FF1 to FF2 and FF2 to FF1 again. And just like that, the bitstreams are merged. You can see the output is already available.
Let's take a look at the decoder in action.
So now that we have our merged bitstream, we can just run the decoder and it will output a YUV file And now that we have the YAV file, we can just use ffplay to make sure that we have the output that we expect. So as you can see, we have the output that we expected, and we also have a frame synced output between all the merged bitstreams.
Thanks for watching. If you have any questions, please feel free to contact us, and if you're curious about what we do, visit our website.